To express the orthogonality between two vectors, let ei dot ej, we have used the Kronecker delta ij, where delta ij were defined to be is equal to 1 if I is equal to j and is 0 if I not equal to j. Here the suffixes that are used in connection with the Kronecker delta are the discrete suffix. For three-dimensional case, I and j can have values 1, 2, 3. For the continuum analog of the Kronecker delta is known as the Dirac delta function. Although this is not an analytical function of mathematics, by analytical function we mean a function which is finite in a range and its all higher derivative exists, and for which a Taylor series expansion is possible. It is the analytical function. The Dirac delta function that we are going to introduce is not an analytical function. Still, it is a very important concept which is used extensively in physics and mathematics. If we want to say express the charge density of a system comprising of few point charges, then the charge density can be represented as a delta function. Now let me define Dirac delta function. The formal definition of Dirac delta function is that if we define delta function as x minus x0, this is defined as 0 if x is not equal to x0, and it goes to infinity if x is equal to x0. And this definition is supplemented by the normalization condition is that delta x minus x0 dx over all x is equal to 1. This is known as normalization condition. So if we consider these two, we may visualize a delta function as if a function which is picked at around x0 and the width dx is vanishingly small. So the peak value of the delta function tends to infinity, and width of delta function tends to 0, so that the area under the curve is finite. The area under the curve is finite and which is taken to be 1. This is the normalization condition. We can visualize the delta function concept like this. Let us consider that we have a drop of liquid. So this liquid has a finite volume, and we are sucking this liquid by a very long tube of vanishingly small width, such that at a the entire tube is filled with the liquid. So the liquid column has a very high height. At the same time, the width or the cross-sectional area of this tube is very small, so that the volume of this tube is equal to the volume of the liquid drop. So which is a finite quantity. This is one way of visualizing delta function. The delta function has few other properties too, which are the other properties of delta function is that the scaling power, the shifting property, the shifting property, by means of shifting property we mean f of x delta of x minus x0 dx integrated over all x is equal to f of x0, where x0 is a continuous, f is a continuous function, and if we mm, draw the graph, this is the function, this is x, this is x is equal to x0, and the delta function is of this sort. It is, and let us consider the function f is this. This is the delta function, and this is the profile of function f. So, for all values of x which is not equal to x0, delta function is 0, and since fx is finite, finite quantity multiplied by 0 is 0. So, entire part, if we consider the product of f with delta is 0 everywhere except this, and near x is equal to x0, the function f can be represented by its average value over this vanishingly small width on which the value is f of x0, and the remaining quantity is integration of delta x minus x0 dx, which is 1. So this result follows. This property is known as shifting property. This is normalization, this is shifting property. Then there is a another function f of x operated by delta of ax minus x0 dx. This is this result is f of x0 by mod a, which immediately suggests that delta of ax minus x0 is equal to delta of x minus x0 divided by mod a. To prove this, let us call this part as, this part is, we define y is equal to ax, so that this quantity becomes integration over all space f of x delta of ax minus x0 dx becomes f of y by a delta of y minus y0 d of y by a. And if we take y by a out, this is 1 by a, and this is f of y0 by a. F of y0 by a is f of x0, so this is 1 by a f of x0. Now it will be shown that delta function is an even function, so this is valid for positive as well as negative values of a, so we put a modular sign over it. The another properties is the delta function involving its derivative. So this is known as scaling property. Then we have integration f of x delta prime of x minus x0 dx. This is equal to minus delta of x minus x0 . This is equal to minus f prime of x0, which follows if we immediately if we integrate it. So this is over all x. If we integrate this by parts, the left hand side, if we integrate by parts and consider this is the first function, so this is f of x delta of x minus x0 with limits, upper limit say lower limit minus infinity, upper limit plus infinity, which is 0. The delta function is 0 everywhere except at x is equal to 0, so this part is 0. And then we have in all x this is f prime of x times delta of x minus x0 dx, and if we use this property, the shifting property of delta function, this is equal to simply minus f prime of x0. And still now we have used delta function which is defined over entire range. We may have encountered delta function which is integrated over a finite range. So this condition will be different. So this is delta of x minus x0 dx is equal to 1 over all x. This was the definition. If we change this one to like this, consider integration from a to b delta of x minus x0 dx. So what will be the result? This is very important, and this result is applicable when we use delta function over finite range. This is equal to 0 if x0 does not belong to the interval AB. Sorry, open interval AB. This means either A and B both less than x0, or A and B both greater than x0. In this case, the result is thus. It is equal to half if x0 is equal to A or x0 is equal to B, and this is 1 if x0 lies in between AB. So you note the change in definition. This is the delta function defined over all x, and when we use it over finite range, this is the definition of delta function. Consequently, the shifting property also changes. The shifting property is integration fx delta x minus x0, integration from a to b f of x delta x minus x0 dx. This becomes f of x0 times 0 if x0 does not belong to interval AB. This is half if x0 is equal to A or x0 is equal to B, and this is 1 if x0 lies in AB. This is the few important properties of delta function. As we have stated earlier, one more thing I have forgot to mention, the evenness of delta function. That is, evenness of delta function means delta of x minus x0 is equal to delta of minus x minus x0 is equal to delta of x0 minus x. Which follows immediately either from this definition or from the shifting property. As I have stated earlier, that the delta function by its definition is not analytic function. So the mathematical expression for delta function is very difficult. So to represent delta function by mathematical relation, what we do, we use a certain function which depends on n, and as n increases, the function approaches more and more to delta function. This is called the sequential delta function. Remember once more, there is no exact expression for the delta function, as it is not an analytical function. In literature or in textbook, it is called the generalized function. Uh, so, but for mathematical purpose, we need to use few specific form of delta function which satisfies few of the properties of the delta function. So this is known as sequential delta function. This is delta n. So what we do in delta n x minus x0 is represented by a known function. Known function depending on n such that as n tends to infinity, peak of delta n tends to infinity and width tends to 0, so that the area under the curve is a finite one. This is known as sequential delta function and is represented as delta n x minus x0. To simplify mathematics, we use delta n of x, and this from here to there we can just go by a change of origin of the coordinate system. The representation is the rectangles. This is Rn of x is defined as n if x lies between +1 and is 0 otherwise. So this is like this. This is Rn, plot of Rn. The width is like this. So this is the width. If we change the width, in this way, as n increases, this width is 1 upon n. So this 1 upon n goes to 0 and the height of the peak value increases, and so that the area under the curve is always 1. This is one representation of delta function. There is another isosceles triangles. Isosceles triangles. This is Tn of x. To write the mathematical form, we write it like this. This is the expression of Tn of x. This is symmetrically placed above the origin, and the width is this width is 1 by n and plus minus. This is 1 upon n, this is minus 1 upon n. So the base is 2n. The base of the triangle is 2n, and the height is adjusted is n, and so that the area of the triangle is this. So for this part, you see that the function has to be 1 upon nx for x less than 0 greater than minus 1 upon n. This is n1 minus nx when x is less than 1 upon n and greater than 0 and 0 otherwise. This is the sequential representation of delta function with triangles. If we choose another n value, then the triangle will be like this. This is for one n and this is for another n, and always the area under the curve is 1. There are another important representation is the Gaussian Gaussian function Gn of x. Gn of x is the constant part is n upon root pi e to the power minus n square xs square. This is the Gaussian. The Gaussian curve is like this. At x is equal to 0, the peak value is n upon root pi, and the Gaussian curve is this is for a lower value of n. For a higher value of n, the curve will be like this, and as n increases, the peak value increases. And is the sin c representation, sin c function. This function arises in connection with the diffraction of single slit pattern. This is given by sine of nx upon n pi, pi of x. Sin c function is given by pi of x. It can also be written as 1 upon 2 pi integration e to the power I kx dk from minus n to plus n. If we integrate this, you will get this result. There are another exponential function. Exponential sequential representation is given by en of x. En of x is n by 2 e to the power minus n mod x. This mod x is required because if we plot this in the positive range, n minus e to the power minus nx will fall, and in this part it will have a rise. To eliminate this rise and to make the curve symmetric about x is equal to 0, this mod x part is included. And lastly, I will mention a very important representation. This is the Lorentz representation, the Lorentzian. This is a very important, and we shall use these to prove the few properties of delta function. We shall prove few properties of the delta function using the Lorentzian sequential Lorentzian representation. Now we have ln ln of x minus x0 is equal to n by pi into 1 plus n square x minus x0 square upon 1. Now, this is the sequential delta n of x minus x0. We first calculate the integration in, which is ln of x minus x0 dx integrated from a to b. This is n upon pi integration dx 1 plus n square x minus x0 square integrated from a to b. We make a substitution that n x minus x0 is equal to tan theta, so that n dx is equal to sec square theta d theta, and the denominator 1 plus n square x minus x0 square is equal to sec square theta. So this becomes n by pi sec square theta d theta by sec square theta integrated from theta a to theta b, where we define theta a, we define with theta a is defined as tan of theta a is equal to n a minus x0, and tan of theta b is n b minus x0. The result is n by pi. Oh, there is one factor I have missed. Dx is 1 by n. We substituted that n x minus x0 is equal to tan theta. So n dx is equal to sec square theta d theta. So dx is 1 by n. So there will be one n factor which makes it 1 upon pi and d theta integrated from theta a to theta b. So this is 1 upon pi theta b minus theta a. Now consider few cases. 1. If x0 is less than both a and b, x0 is less than both a and b, in which case this is negative, this is negative, x0, sorry, this is positive, x0 is less than this, so theta a is positive, theta b is also positive, and when n tends to 0, n tends to infinity, this tends to plus infinity, this tends to plus infinity, that is theta a tends to plus pi by 2 and theta b tends to plus pi by 2. As n tends to infinity, theta a tends to plus pi by 2, theta b tends to plus pi by 2, and in tends to 0, or in is equal to 0. Let me explain once more. Tan of n a minus x0, this part tends to infinity because in x this is non-zero, and when we multiply it by n this is infinity, and x0 is less than a, so this tends to plus infinity, which implies that theta a tends to plus pi by 2 as theta tends to tan of theta tends to plus infinity as as theta tends to pi by 2. Secondly, if x0 greater than both a and b, in which case you see that theta a and theta b both are negative because x0 is greater than both a and b, and as n tends to infinity, theta a tends to minus pi by 2 and theta b tends to minus pi by 2. So again, in tends to 0. Third, if x0 is equal to a, if x0 is equal to a, then this theta a is 0 and b is greater than a, so this part tends to plus pi by 2. This part tends to pi by 2. Theta a is equal to 0, and as n tends to infinity, theta b tends to pi by 2, so in tends to half because it is pi by 2 and there is a pi. If x0 is equal to b, in which case theta b is equal to 0, theta b is equal to 0, and as n tends to infinity, theta a tends to minus pi by 2, and again in is equal to half because minus or minus, this is 0 and this is minus or minus pi by 2, and which cancels out. And finally, if x0 lies between b and a, x0 lies between b and a, in which case as n tends to infinity, theta a tends to minus pi by 2 because this is negative. x0 is greater than a, so this is negative but this is positive, and theta b tends to plus pi by 2 so that in is equal to 1. So here we have proved the shifting property in terms of Lorentzian, and it is a easy touch to show that the normalization condition is indeed obeyed by this fact. So here we have considered the Lorentzian function to define a very important property of delta function. In general, this part is not referred in most of the text, but it is a very important concept when one uses delta function over a finite range. Whenever one uses it over an infinite range which covers all values of x only, this property is of relevance. But when we use it over finite range, the first 4 points becomes very important. To conclude this lecture, the first lecture on Dirac's delta function, we shall just mention the integral representation of delta function. We shall not go into the proof of it, which you will learn in mathematical physics 2 course through Fourier transform. The integral representation of delta function is this. The integral representation of delta function is delta x minus x0 is 1 upon all over all space of K. This is known as integral representation. Uh, if we perform the integration, then we will have 1 upon 2 pi, and then we have integrated over this K. So in the numerator we will have I x minus x0, and you will have e to the power I k x minus x0 integral. This we do in this way: 1 upon root 2 pi, 1 upon I x minus x0, but the limit n tends to infinity, e to the power I n x minus x0 from minus n to plus n. So this becomes x minus x0, and we have e to the power, limit n tends to infinity, this is equal to, this is cos plus I sine, this is cos minus I sine, so this is twice I sine of n x minus x0. So we will have this I cancels out, this is 2 by pi, 2 by pi, and then we have sine of n x minus x0 by x minus x0, and limit n tends to infinity, which is the basics of sine C representation. Sine and C representation is obtained from this consideration. In the next lecture on Dirac delta function, we shall extend the concept of Dirac delta function to 2 dimension in 2 and 3 dimension in Cartesian coordinates, as well as in other curvilinear coordinates.